Hi, welcome to acid-base chemistry. So today is going to be part one of acid-base chemistry. We're going to introduce acids and bases and talk about what makes a strong acid versus a weak acid and how we deal with those in a chemical reaction and how we're going to apply it to equilibrium systems. Okay, so here are our objectives today. We're going to learn the three types of acid-base definitions. So there's three ways that we can define an acid-base. We're going to learn to identify conjugate acid-base pairs in a chemical reaction. And this is going to be really important as we move into the next chapter as well, as being able to understand the conjugate acid-base pairs in a chemical system. Understand factors that affect acid strength. So there's two primary factors that are going to affect acid strength. We're going to learn those today. We're going to learn the 6 strong acids. I do encourage you to learn the 6 strong acids because once you know the 6 strong, then everything else is a weak acid, which is kind of nice. And then we're going to learn to write Ka. So Ka, remembers, our equilibrium constant. Ka and Kb dissociation equations. So that's our lineup for today. So I thought before we do this, because it might have been a little while since you thought about acid-base chemistry, let's just back up and talk about nomenclature first. Just a brief review on nomenclature. I know I said we weren't going to do any chemical nomenclature, but we'll do just this little bit here. Acids we identify because they generally start with a hydrogen plus a nonmetal or hydrogen plus a polyatomic ion. Those are going to be our acids. And so to name those, we're going to name them 2 different ways. Our naming tree is going to be, is there oxygen present in the formula? So if the answer is no, then I have just what we call a binary acid, and it's hydrogen plus a nonmetal. Some examples of this might be HCl, HBr, HI, H3N. So these would all be acids, like a binary acid where there's no oxygen in it. So if I have a binary acid, I'm going to start the name with hydro plus my nonmetal, but I'm going to change the ending to ic, and I'm going to add acid at the end of that. So my nomenclature for this would be hydrochloric acid or hydrobromic acid. Hydrochloric. So when I see hydro here, that means there's no oxygen in that acid. If I do have oxygen, so let's say, yes, there's oxygen present, then I have an oxoacid. And an oxoacid is hydrogen plus a polyatomic ion, because most of our polyatomic ions are going to have oxygen in them. So to name these, first off, there's no hydro. So I'm not going to start it with hydro. I'm going to start it with the polyatomic ion name, and then I'm going to change the ending. If the polyatomic ion ends in ate, I'm going to change it to ic. If it ends in ite, I'm going to change it to OUS. So that's going to be our nomenclature, our simple nomenclature between a binary acid and an oxoacid. So something like this, for instance, H2SO4, this is the sulfate polyatomic ion, so this would be sulfuric acid. H2SO3, this is the sulfite polyatomic ion, so this would be sulfurous acid. So you'll notice here that this ends in ate, so this ends in ic, and this ends in ite, so this is going to end in OUS. And that's going to be how we're going to tell these acids apart, because oftentimes you're just going to be given the name of the acid, and if you can remember the nomenclature, it's going to help you to write the chemical formula. A couple of things is that there are some exceptions. So for instance, HCN is not necessarily a binary acid because CN is a polyatomic ion, but there's no oxygen here. So this would be an exception, and this would be hydrocyanic acid because this would be the cyanide polyatomic ion. So there are a couple exceptions to acid nomenclature. All right, so some common acids. We are exposed to acids a lot. Acids are generally found in a lot of our foods. Acid gives us that sour taste. And we can generally recognize these because they begin with hydrogen. So here are some common acids. So here's hydrochloric. We use this a lot in the lab. Sulfuric, nitric. So we didn't really talk about, but nitric is an oxoacid. It has that oxygen here in the nitrate polyatomic ion. So this is nitric acid. Acetic acid. This is an organic acid. This is a very common acid. Citric acid, carbonic acid, hydrofluoric acid, phosphoric acid. So these are some common acids, and you notice that they each have a hydrogen in them. Structures of acids. So if we move into things that are less simple than just a binary acid, where here I just have a bond between the hydrogen and the chlorine, if I look at the structure of acids, things that have a polyatomic ion, obviously they have that polyatomic ion root, and so that doesn't break up. So the sulfate ion is S bound to 4 oxygens. And so you see I still have the sulfate polyatomic ion, but what I have here is attached to the oxygens are these hydrogens. And these are the hydrogens that make this an acid, because these hydrogens that are attached to the oxygen are going to be the hydrogens that are going to be lost when that acid dissociates. And so we call these the ionizing hydrogens. These are the acidic hydrogens. They have various names, but those are the hydrogens that are going to come off when this acid reacts. Nitric acid, so here's the nitrate polyatomic ion, NO3, and then here's that ionizing hydrogen attached to the oxygen. And then things that like organic acids have this, we call it a carboxylic acid group here, which is C double bonded to O, single bonded to oxygen, which is then bound to the ionizing hydrogen. So in acetic acid is only going to lose 1 hydrogen, even though it has 4 in its structure, because it's only going to lose this hydrogen that's bound to the oxygen. So in oxo acids, the hydrogen that's bound to the oxygen is the hydrogen that's going to come off. In a binary acid, you only have a hydrogen and a nonmetal, so obviously the hydrogen is going to be the one that gets lost. So common acids. Common bases, some common bases, and so we recognize base. Typically in 150 you recognize base based on the hydroxyl group. So it's a group 1A metal bound to a hydroxyl group, or a group 2A metal bound to a hydroxyl group. So in this chapter we're going to introduce a broader definition of bases, which is going to encompass things that don't necessarily have the hydroxyl group as part of their chemical formula. So here you can see a couple of them: sodium bicarbonate, this is also called sodium hydrogen carbonate, sodium carbonate, ammonia. These are all bases as well. They don't look like bases, but they behave very much like bases in a chemical reaction. And so that brings us to defining acids and bases. So there's 3 ways that we can define an acid and a base. So the first way that we're going to define an acid is called the Arrhenius acid, and this is the oldest definition. And this was introduced in the late 1800s. An Arrhenius acid base is simply, an acid is something that produces hydrogen ion in water. So an acid is anything that's going to produce a hydrogen ion in water. A base is any substance that produces a hydroxyl group in water. And so what you notice is this Arrhenius definition is really an aqueous definition. It's happening in water, which is okay because a lot of the chemical reactions that we deal with happen in water, but not all of them. So this is kind of a simple way of looking at an acid base. So here's what I mean by producing these ions. So what you see is if I have HCl, and I add that to water. So now it's going to be HCl aqueous solution. But what really is happening is I have hydrogen ions in water and I have chlorine ions in water. So this is behaving very much like an ionic compound when I dissolve it in water, in that it breaks apart into ions. The same thing with a base. The base is going to produce hydroxide ions. If I look at a really simple base, like sodium hydroxide here, then this hydroxyl group is going to break apart and the sodium group is going to break apart, and it's going to form these ions in the solution. So in Arrhenius definition, you're really producing hydrogen ion, you're producing hydroxide ion when you take a substance and you dissolve it in water, you add it to water. Our second definition is called the Bronsted-Lowry. So this was our first definition, the Arrhenius acid base. Bronsted-Lowry is a broader definition. It's named after 2 guys. And this was introduced in the 1920s, is when the Bronsted-Lowry definition came about. In a Bronsted-Lowry definition, an acid is something that is going to donate hydrogen ions to another substance. So we call those proton donors. A base is the opposite. A base is going to accept hydrogen ions from another substance, and we call those proton acceptors. So let's think about why we're calling this protons. So a proton is a subatomic particle. There's three. There's electrons, neutrons, and protons. And proton is used interchangeably with H plus, because what happens when hydrogen loses an electron and it forms this hydrogen ion? So let's say I have HCl. HCl is going to break apart into hydrogen ions and chloride ions. So that electron has gone with chlorine. This here, because hydrogen only has one proton, one electron, and 0 to 2 neutrons, depending upon the isotope. If it loses that electron, the only thing that's really left in the nucleus is a proton and maybe 1 or 2 or none neutrons in that system. And so we would call this hydrogen ion to signify that it's lost an electron, or just a proton. Or if it's in water, we're going to call it the hydronium ion. Because in water, if this is an aqueous solution, in water this is this really small hydrogen ion, this plus proton here, is going to bump into a water molecule and they're going to form H3O plus. And so this is the hydronium ion. So in water, you never just have hydrogen ion floating around, you have hydronium ion in water. If I have something else where I'm not in an aqueous solution, then I would just have hydrogen ion. So you'll see these either written as a hydrogen ion, as a proton, or as the hydronium ion, and they all mean the same thing. So Bronsted-Lowry definition. And this is going to expand. So this expands past aqueous solutions. So now I don't need water present to be able to define an acid base. So all Arrhenius acid bases are also Bronsted-Lowry acid bases, because in water, if it's going to produce hydrogen ion, it's donating that hydrogen ion. Base is going to produce hydroxide ion. That hydroxide ion is going to react with the hydrogen ion to form water, so that's going to accept a proton. So all reactions that fit the Arrhenius definition will also fit the Bronsted-Lowry, but not all acid bases that fit the Bronsted-Lowry definition will fit the Arrhenius definition. So this is specific just to water. Okay, so let's look at our third definition. So we have Arrhenius definition, we have Bronsted-Lowry, and our third definition is called a Lewis acid base. This is our newest definition, and this has to do with the transfer of an electron pair. So Lewis acid bases kind of deviate from how we think about it, because now I'm no longer need to define my acid in terms of a proton. So I'm moving away from the proton transfer definition. So I'm not looking necessarily at a proton. So Lewis acids and bases we don't really cover at all in this chapter. I just want to introduce this because this is the third way that we identify an acid base. And then we're not going to really touch on this until closer to the end of the semester, where we talk about transition metal chemistry. I'm going to define a Lewis acid as an electron pair acceptor, and my base is going to be an electron pair donor. Let's say I take hydrogen ion and I react that with NH3. NH3 has a chemical structure where there's a lone electron pair on nitrogen. If I allow these two to come together, what's going to happen is I'm going to form NH4, and it's going to look like this because this hydrogen ion has accepted an electron pair from nitrogen and formed this Lewis acid base adduct. I have to have a lone electron pair on the central atom of that to be an electron pair donor. This is going to be my electron pair acceptor. So anything that has space to accept an electron pair and the ability to get in, so it's not huge, it can be a Lewis acid. Anything that has a lone electron pair on the central atom that has the space so that this acid can get in close to it can be a Lewis base. And then this whole thing here is called a Lewis base adduct, meaning it's this complex. So I don't necessarily need hydrogen. I could also do this with, say, something like BF3. Draw the Lewis dot structure. I know you guys thought you were done with Lewis dot structures, but this is where the Lewis acid comes in. Same guy. If I draw my Lewis dot structure for BF3, what I see is that I have boron can still hold 2 more electrons. So it only has 6 electrons around it. And so it's able to act like a Lewis acid. If I allow that to bind with, say, NH3, NH3 can donate this electron pair, and it doesn't really donate because it keeps it, and then it's going to form this BF3 NH3 Lewis acid base adduct, where this is my acid and this is my base and this is my new compound. So I need an empty orbital here for this to happen, and I need a lone electron pair on my central atom. And if I have those two conditions, then I have the ability to form this Lewis acid base construct. Another thing that can do these Lewis acid bases, this is the last thing I'm going to talk about with these, and then like I said, we're not really going to come back to them, is if I have an ion, a metal ion, and let's say I have that in solution. So if I have aluminum ion in solution, water happens to have two lone electron pairs on oxygen. So this can be since aluminum has lost 3 electrons, it has empty orbitals. Oxygen and water here has a lone electron pair. It can only share one just because of this space that's available. And I could form this AlOH2 6 aqueous 3 plus adduct. And you're like, what? What does that look like? This actually means that this aluminum has so many empty orbitals. It doesn't just have one, it has a lot more empty orbitals because it's lost all of its valence electrons. It can actually bind 6 water molecules. And it would look something like this. If I had aluminum here, then I would have an oxygen here. So this is the lone electron pair on that oxygen is being shared with aluminum here. I could have the same thing down here. And then I'm going to have this octahedral electronic geometry. And so you can see that these can be fairly complex. And so aluminum here has formed a Lewis acid base adduct with 6 water molecules. And this whole thing is my entire adduct. And so this is going to be my Lewis acid because it has these empty orbitals, and each of these oxygens with this lone electron pair is going to be my Lewis base, and it's going to donate that. So Lewis acid base chemistry can get pretty complicated. So we're going to move away from that and not really come back to it in this chapter. All right, let's go back to Arrhenius definition. Let's talk about what's happening when you add an acid to water. So Arrhenius definition was that if I add an acid to water, that it's going to dissociate into hydrogen ions. If I take HCl and I add that to water, this is like our slide, I'm going to form hydrogen ions and I'm going to form chlorine ions. And I said because water is hanging around because this is an aqueous solution, this really is going to form the hydronium ion. This lone proton here is going to glom onto water, much like an acid-base adduct, and form the hydronium ion. So this would be an Arrhenius acid. It produced hydrogen ion in water. If I take HF, for instance, and I have, so this is hydrochloric acid, this is hydrofluoric acid, and I add HF to water, I'm going to form hydrogen ion, sure, and fluorine ion, of course, and this is really going to form the hydronium ion, and this came from HF. But what happens is HF doesn't dissociate very well, so only a small amount dissociates. So this is an opportunity to have an equilibrium scenario. And you have an equilibrium scenario for things like HF because it doesn't fully dissociate into ions. So if it doesn't fully dissociate into ions, we have a name for that. We call that a weak acid. It's not going to be that reactive. HCl, however, fully dissociates, meaning there's no HCl left, there's only hydrogen ions and chloride ions in solution, and so this we would call a strong acid. So the difference between a strong acid and a weak acid is how much it dissociates. So strong acids will fully dissociate, meaning that this is a one-way street. I add this to water, I'm going to have hydrogen ions, I'm going to have chlorine ions. These are not going to reform into HCl. If I have a weak acid, now I have an equilibrium. and I have all these things present. I have hydrofluoric acid that's undissociated, I have hydrogen ions, and I have fluoride ions, and I have all of that in solution. And so that's going to be a weak acid. Same thing can happen with a base. So I can have a strong base and I can have a weak base. So strong base might be something like NaOH, sodium hydroxide. If I add that into water, I'm going to form sodium ions and hydroxide ions, and that's going to be complete. So this is going to fully disassociate. That makes it a strong base. Now we can have the same thing happen where I have a weak base. And so NH3, ammonia, is a perfect example of a weak base. So, and it also doesn't look much like a base because it doesn't have that characteristic hydroxyl group here. So if I have this, and I'm going to just add water into my equation here. Water's not aqueous, it's a liquid. What's going to happen is my definition of a base, according to my Arrhenius definition, is that it's something that's going to produce hydroxide ions in water. And so we can still operate under that because we're in this aqueous solution here. So if this is going to produce hydroxide ions in water, what's left over is a hydrogen from here is going to bind onto here and form NH4 plus that ammonium polyatomic ion. And this is a scenario where this is going to be weak. And so I'm going to have some of it dissociate and form hydroxide ions, but I'm going to have some of it that's just going to stay ammonia. So this would be an example of a partially dissociates, and we'll call that a weak base. So I can define acid strength and base strength based on how much they dissociate in solution. So things that fully dissociate are going to be strong, and things that are weakly dissociate are going to be weak. Now, if I think about the Bronsted-Lowry definition, things are going to accept protons and things are going to donate protons. So an acid is a proton donor and a base is a proton acceptor. So if we look at this scenario here where I have NH3 reacting with water to form hydroxide and NH4, there's been a proton transfer. So the proton has left water and gone to here. So this is going to be my base because it's a proton acceptor, and this is going to be my acid. I don't think of water as an acid because it's my proton donor. So this is where the Bronsted-Lowry definition is going to expand our definition of an acid base because it's based on the chemistry, what's happening in a chemical reaction, what's happening to that proton. Whatever is donating the proton, that's going to be the acid. What's accepting the proton, that's going to be the base. If this is my base, then if I come over here on this side, because this is an equilibrium scenario, I can have the reaction going in the opposite direction too. So I have it written as if it's going forward. This is my base, this is my acid. But what's happening if the reaction goes in reverse? This now is going to be my proton acceptor. So this is going to act like my base. That means that the hydroxyl group will accept a proton from ammonium ion to reform water. And since this is going to lose a proton, this is going to be my proton donor. This is my acid. Now you'll notice in this I have two acid-base pairs. So NH3, ammonia acts like a base, but ammonium acts like an acid. Water acts like an acid, but hydroxide acts like a base. So these are what we call acid-base pairs. So NH3 and NH4 then are going to be something we call a conjugate acid-base pair, meaning it acts like a base on this side and an acid on this side. My water here and my hydroxyl group are also a conjugate acid-base pair because it acts like an acid until it loses a proton, and then it acts like a base. Conjugate acid-base pairs are related to each other by the gain or loss of a proton. If I just have plain water, I react water with itself. So I just have pure, good old-fashioned water. It's going to do this auto-ionization where it forms this here. This is an equilibrium scenario. It has an equilibrium constant, and it's really, really small. So if I just have a pure sample of water, I'm going to have a small amount of hydronium ion and hydroxide ion in that solution because water is going to auto-ionize. This will be my acid, this will be my base, this will be my conjugate acid, and this will be my conjugate base, because this is going to donate a proton, this is going to accept a proton. So my pairs here are going to be this. This is going to be my conjugate acid-base pair, and this is going to be my conjugate acid-base pair for the autoionization of water. And we'll come back to that in a bit. Break this part 1 into 2 parts, so this will conclude part A, and then we will come back together for part B.